We learned earlier in the year and in Algebra 2 that a complex number is of the form a plus bi. In this section, they label it as a letter z because we're going to be working with a couple of different types of complex numbers, and so they're going to start labeling things as like z1, z2, z3, things like that. We're going to draw a picture just to get us back into what a complex number looks like graphically. If I make the coordinate plane, normally you're used to seeing the x and the y-axis. But when you draw complex numbers, don't forget you have a real axis and you have an imaginary axis. And the real axis is the x-axis, your imaginary axis is your y-axis. As we go through, we want to graph a couple of a complex number. And so let me get some points on here. We're dealing with positives for right now, so if I extend this out. But we want to graph the number 4 plus 7i. And if you remember from Algebra 2, that means we go right 4 on the real axis and up 7i on the imaginary axis. So 1, 2, 3, 4, 5, 6, 7. And so this is our complex number z, 4 plus 7i. And again, the real axis goes up by 1s, the imaginary axis goes up by i's. If I wanted to graph the real number 4, you only go on to 4 on the real axis and then put your point. If you want to graph the number 7i on the axis, it's only on the imaginary axis, and you go up to 7i. If you have a negative I value, you go down. If you have a negative real value, you go to the left. So it's like graphing the 0.47. It's just considered a complex number, and we write it in a plus bi form. What we're going to be looking at is, though, how do you find what we call an absolute value or a modulus? And so let me show you in the picture as to what we're asking. An absolute value of a complex number is the distance from the point to the origin. So if I look at z and I go to the origin, the question is, what is this distance? And we call that the absolute value. And the way we write this is the absolute value of z. And so we're questioning what that distance is. Well, like we did in trig, what I can do is draw a right triangle, and we know this is 4, and we know this distance is 7. And in order to use Pythagorean theorem, we don't include the I. And so the way the absolute value of a complex number works is you basically are doing Pythagorean theorem, where you take the square root of a squared plus b squared, but the biggest thing is you don't include the I. Okay, it's just the a and the b, so please be careful as you do that. So if we tried to find the modulus, or the absolute value, for 4 plus 7i, we take the square root of 4 squared plus 7 squared, and 16 plus 49 is the square root of 65. If they want it exact, you leave it as the square root of 65. If they want an approximation, I would say about 8.1. So it kind of depends on what they're asking for. The majority of the time, we're going to leave it in this exact form because we're going to use our angles and our unit circle and our trig stuff again as well. We said above again the modulus for a plus bi is the square root of a squared plus b squared. And so please be careful that you know the words both modulus and absolute value because they will throw either of those out at you. Again, what they're looking for is basically if you draw a right triangle, what is the hypotenuse? Okay. Let's keep going. We're going to start talking about this trig form of a complex number. And I just want to draw you a picture. And I'm going to go back to the idea that we just did before, that if I give you this complex number z in an a plus bi form, I can make this right triangle with the unit circle, knowing that this side is going to be A and this side is going to be B. And I want to bring back this idea because we're talking about trig. We're going to go back to this idea of theta. If this is theta, then this is going to be the radius of my circle if I were to make a circle. And your book seems to like the R for that. Okay? So here's what's happening. If I give you, given the modulus and the angle, okay, we want to know things about A and B. So I'm going to write an equation using my modulus, which is r, and my angle, and I'm going to rewrite a and b. So let's talk about a first. Well, if I need to find a, but I know my angle and my r, a is the adjacent side, r is the hypotenuse. And so I'm going to start by saying the cosine of my angle is a over r. If I rewrite this, then a is the same thing as r times the cosine of my angle. All right, let's go with b. b is the opposite side, so I know that the sine of my angle is b over r. And again, I can rewrite b as r times the sine of my angle. Okay, so we want to write a complex number. So we have this complex number a plus bi, and our goal is to write this in trig form, so with our cosines and our sines. Okay, well if I write this, let's replace a. A is r times the cosine of my angle, plus b is r times the sine of my angle, and then I have an I. Now, what do they have in common? Well, they each have an r, so I'm going to pull out the r, and I have then the cosine of my angle, plus, and I'm going to put my I first, I sine of my angle. And this, I'm going to make this a little bigger, this is how we write a complex number in trig form. Now, there are going to be times when I know a and b, and I need to find r, and I need to find my angle. So I just want to go back through and make sure we know that. If I'm given a and b, how do I find r and theta? Well, to find r, I use Pythagorean theorem, the square root of a squared plus b squared. To find my angle, if I know a and b, I know the opposite and the adjacent side, so I'm going to inverse tangent the opposite b over a in order to find my angle. Okay, so keep that in mind. If we're given the modulus and the angle, then we're going to have to use sines and cosines. But if we're given a and b, then we're going to find r and theta using Pythagorean theorem and the tangent. Okay, and so this is kind of the process. Again, we're going to be going back and forth from complex form to trig form throughout the chapter. And so take a look. I'm going to give you an example of each. If you look at the first example, we give you the complex number. Okay, now what I'm going to do is draw a little picture here. Because negative 4 means I go left 4, and negative 4i means I go down 4. So my negative 4 minus 4i is right here. Let's call that z. Okay, so if I draw my triangle, here's my right angle. I know that this is negative 4, and I know that this side is negative 4. Well, let's start with the hypotenuse. To find the hypotenuse, I take the square root of negative 4 squared plus negative 4 squared. So 16 and 16 is the square root of 32, but that can be broken down into the square root of 16 and the square root of 2. So my r is 4 square roots of 2. Okay, so that's r. Now, how do I find theta? Okay, well, in order to find theta, I take the inverse tangent, because I have the opposite and the adjacent, of negative 4 over negative 4, which is basically the inverse tangent of 1. And where does the tangent equal 1? Well, I'm in the third quadrant, so what is this angle? My angle then, if I go back to my unit circle, is 225 degrees. And the reason we need 225 is because our coordinate point z is in the third quadrant. So let's write our trig form. Our trig form, let's see, I'm running out of room, but we'll put it down here. It's always, if I look at it, it's r, and the value of r is 4 square roots of 2 times the cosine of my angle plus I times the sine of my angle. And And again, I don't want to simplify this because if I simplify this, I get back to the complex number. And that's not my goal. My goal is just to write it in terms of the trig using the angle and the hypotenuse. Okay, so you've just taken a complex number and gotten it into trig form. We're going to go backwards. I've now given it to you in trig form. We want to go back to complex number form. And this is way easier. This is here's our theta. So as we go through, you're going to need your unit circle. The square root of 10. Now the cosine of pi over 3. So the cosine of 60 degrees is 1/2. The sine of 60 degrees is the square root of 3 over 2. Now I'm going to take this and I'm going to distribute. So I get the square root of 10 over 2 plus square root of 10 times the square root of 3 is the square root of 30 over 2 with an I. Okay, now I don't want to write my I in front. Let's change this a second. So my complex number is the square root of 10 over 2 plus the square root of 30 over 2 with an I. And again, I want the I to come second. Normally we write it in front of the square root, but I want the I to come second because this is A plus BI form. Okay, so keep that in mind. So going from trig form to complex number form is way easier, but we want you to be able to work backwards as well. All right, flip the page. We're going to use these complex numbers as we go through. Let me see if I can slide this down a second. We're going to be multiplying two complex numbers and dividing two complex numbers. And so I'm going to start with the multiplication. When you multiply two complex numbers in trig form, what you want to do is multiply the moduli. So multiply the R values, okay, and add the arguments, and the arguments are your angles. So if I look at it in terms of Z1 and Z2 above, I'm basically taking R1 times R2, and then I'm going to take the cosine, and actually let me make this a bracket so don't confuse, cosine of theta 1 plus theta 2 plus I times the sine of theta 1 plus theta 2. Okay? And again, we want you to remember the rule, and I think it's easier in word form too than trying to memorize the actual formula, but multiply the moduli and add the argument. Okay? When you divide them, similar idea. Instead of multiplying the moduli, we're going to divide the moduli, and instead of adding the argument, we're going to subtract the argument. Okay? Again, moduli is the R's, arguments are the thetas. So let's take a look at what it looks like. R1 divided by R2, brackets again, sorry, cosine of theta 1 minus theta 2 plus I times the sine of theta 1 minus theta 2, and we close our brackets. Now again, take a look at the order. If Z1 comes first, then R1's on top, and theta 1 comes first. So please be careful because sometimes we're going to switch the order on you. Okay? Now take a look at the next example. We give you 3 times the cosine of pi over 6 plus I times the sine of pi over 6 for Z1. Z2 has a modulus of 4 and an argument of 3 pi over 2. And so if we're going to multiply them, let's start by multiplying. We take 3 times 4, and then we're going to do the cosine of pi over 6 plus 3 pi over 2 plus I times the sine of 3 pi over 6 plus 3 pi over 2. Adding them, it's commutative, so it doesn't matter the order, but let me at least make this, and I'll keep the order the same for you guys. Pi over 6 plus 3 pi over 2. Okay, so now I don't care if you do this in radian or degrees. Truthfully, it doesn't matter because you're talking about exact values. Pi over 6 is a 30-degree angle. 3 pi over 2 is 270 degrees. So when I add these together, as I look at this, this is really 300 degrees. Now again, you're going to want your unit circle as we go through. So you basically have 12 times the cosine of 300. Well, the cosine of 300 is 1/2 plus I times the sine of 300 is a negative square root of 3/2. If I distribute this through, you get 6 minus 12 divided by 2 is 6 square roots of 3, and let's put the I in with the 6. So it's 6 minus 6i square roots of 3. Okay. We're going to go the other way. We're going to divide them. So we divide their moduli, and you get 4/3. Now be careful the order, because in this case Z2 comes first, so that means the 4 is going to go on top. And if I look at this now, my 3 pi over 2 is going to come first. So 3 pi over 2 minus a pi over 6 plus I times the sine of 3 pi over 2 minus pi over 6 again. Okay, now let's take a look at this. If you take 270 minus 30, this is really saying, okay, 240 degrees. And I know we're more comfortable in degree mode, which is fine. Please know that if you have to go to a complex number, though, most of the time we're going to want it in a radian form. Okay, so let's take a look at this. 4/3, we're going to multiply by the cosine of 240 degrees is negative 1/2. The sine of 240 degrees is a negative square root of 3/2. So if I distribute this through, looks like we're going to have to do a little simplifying. So we get negative 4/6 minus, if I distribute it this way, you get negative 4 square roots of 3/6 with an I. Now let's reduce our fractions, shall we? You end up getting negative 2/3 minus 2 square roots of 3/3i. So you're taking this and you're reducing these numbers in your fractions. Again, the I goes at the end because you want it in A plus BI form. In this case here, I guess if you look at the one before it, if you said 6 minus 6 square roots of 3i, that would be okay too. I'm kind of flexible because normally mathematically we put the I in front of the root. I'm okay with it being in either position, so just be aware of that. I'll go with either. Okay, so that's the idea of dividing complex numbers and multiplying complex numbers. And it truthfully is much easier to do it this way than to FOIL an A plus BI with an A plus BI. Okay, now we want to talk in the last idea about powers of complex numbers. And if you look, we know that one z, just one complex number z, is r times the cosine of theta plus I times the sine of theta. What ends up happening is if I took z squared, okay, which is just z times z, let me show you what happens. We would say multiply the moduli, so r times r, and then you'd add the argument. So cosine of theta plus I times the sine of theta plus theta. So you end up getting r squared cosine of 2 theta plus I times the sine of 2 theta. And so I'm going to show you kind of the pattern as we go through, but that's what I wanted you to see first. Now if I took this and then multiplied by another z, you'd end up getting r cubed. Oh, they did the 4th. I'm sorry, let's try this again. You'd get r to the 4th, and then you'd get the cosine of 4 theta plus I times the sine of 4 theta. And so what we want you to see is there's a relationship between the exponent of the complex number and what it does inside to the moduli and the argument. And so if you take any nth complex number, what you end up getting is r to the n power, and then the cosine of n theta plus I times the sine of n theta. Okay, and so you multiply the argument by whatever your exponent is, and you raise the moduli to that exponent as well. Now, take a look at the example below. Okay, now, if we gave you this, you would have to multiply 1 plus 1i 6 different times together. And that's a lot of FOIL. You could use Pascal's triangle if you wanted in combinations, but it still takes a lot of time. What's quicker is if I use what we call de Moivre's theorem, this theorem right here, that says basically, if you put it in a complex number, it's way easier to raise it to a power than FOILing it out 6 times. So we're going to take this to trig form. So I'm going to make a triangle. 1 plus 1i is 1 plus 1i. And if I think about, I need then the angle and I need the r. Okay, so to find the r, the square root of 1 squared plus 1 squared is the square root of 2. And to find my theta, I inverse tangent 1 over 1, which we know if the sides are the same, then the angle has to be 45 degrees. Okay, so in trig form, let's write that first. In trig form, we have the square root of 2 times the cosine of 45 plus I times the sine of 45. Okay, if this is my normal trig form, then we're going to take this this complex number and raise it to the 6th power, which means we take the square root of 2 to the 6th power, and we take the cosine of 6 times 45 plus I times the sine of 6 times 45. All right, well, the square root of 2 to the 6th power is just 8. And this ends up being then the cosine of 270 plus I times the sine of 270. And the cosine of 270 is 0. The sine of 270 is -1, so this is negative I. And if I multiply it by 8, 8 times 0 is 0, 8 times the negative I, the answer is negative 8I. And again, this is way easier to find it like this than it would be to take 1 plus I and multiply it out, FOIL it out 6 different times. Okay? So there are some advantages to using complex numbers in a trig form. Exponents is one of the hugest reasons that we do this. Again, it's easier also to multiply complex numbers and divide complex numbers because you don't have to worry about conjugates or anything like that. And we'll do more of that in class, but this is 6.5, the end of chapter 6. Again, come with questions, concerns, what ifs, anything you have in class.